Well, hey folks, how y'all doing? We are the second day of our review for the um, exam that's tomorrow. Let me mention a couple things about the exam before we get started. Um, the exam is going to there are going to be two exams, and you can take either one. They'll be slightly different, same concepts with some different ideas. Exam, let's say call it A, will be open from 9 a.m. to 2:30 p.m. And then exam B will be open from 3:30 p.m. to 9 p.m. Um, and except for that, I'm not changing anything else. You can still bring a formula sheet with you to the exam. Um, you want to go ahead and finish that formula sheet up tonight and then have it ready for you for the exam. Um, I'm leaving myself a 1 hour window in between to handle um, changing everything out on the website because I'll have to do that manually, and I want to make sure I have time to do that and make sure it works. So that's why I'm stopping at 2:30 and starting at 3:30, and so I've got a little bit of time to manually change the forms over. So it's my hope that um, by shortening the window that any particular set of questions is out, that it will be less effective for people to um, you know post an answer and wait for an answer. That there's not going to be as much window for that. Um, and if I do find um, that people have been sharing things online, I will turn them in just like I did this time, and I hope that doesn't happen though. But that by having two windows, a morning window and an afternoon window, people will still have the same flexibility they had before to sort of schedule when they were going to take the exam. Um, so I'm hoping that this is going to work for people. Um, and with that started, let's go ahead and take a look at the hospital matching problem here. This is number 8. Um, Fred, Elena, Hassan, and Phoebe have applied to residency programs, and so have David and Aaron. They've applied as a couple. Here are their rank lists um, for the hospitals. How do we match everything up? So let's look at the hospitals. The hospitals are Mercy, City, General, and State. And I should also mention this scrolled on to the next page that Mercy and City have 2 positions and General and State only have 1 position. So Mercy and City have 2 positions, General and State have 1. Okay. So let's look at these 4 hospitals: Mercy, City, General, and State. I'm going to remind myself of the capacity of the programs here. All right. So in round 1, almost everybody applies at City. Um, Fred applies at City, Elena applies at City, Phoebe applies at City, David applies at City, Aaron applies at City. So Fred, Elena, Phoebe, David, and Aaron. We have 2 names that start with E, so I've got to be careful about those. But Hassan applies over at Mercy. Um, Hassan is acceptable by Mercy, and so they're not going to reject him. But City has to pare down to 2. So the first name that they cross off is Fred. Um, the second name they cross off is David, but David and Aaron are tied together. So they have to cross off both names together, and that gets them down to 2. Um, Notice that Aaron would have placed higher than Elena, but Aaron was tied to David in the algorithm, and so once David got disqualified, Aaron got disqualified also. Um, so we're left with these 3, and now we have to send Fred got placed out, and David and Aaron got placed out. So we're going to try Fred's second choice, which is General, and David and Aaron's second choice would be David at General and Aaron at City. Okay. So General did not rank David at all. In fact, they didn't rank David or Fred. And so both David and Fred do not place in general. And since they can't place in general, Aaron can't place in city. And so city doesn't have any reason why they need to bump Elena. Because Aaron is going to get bumped from city anyway. And so Aaron and David and Fred all have to go to their third choice now. Fred applies at state, David applies at city, and Aaron applies at general. Fred is acceptable to state. Aaron is acceptable at general. David is acceptable at city, but not preferred to Phoebe or Elena. Phoebe and Elena are higher choices than David. And so David doesn't place there, which means Aaron doesn't place at general either. So then the next choice for David and Aaron are Mercy and State. David at Mercy and Aaron at State. But Aaron was not ranked by State. State does not find Aaron to be acceptable at all. And so that pairing doesn't work out. The next thing they'll try to do is they both try to place at Mercy, David and Aaron. But Hassan is related higher than Aaron. And so with these three people here, Aaron is the lowest placed of them, and so David leaves also. And so that doesn't work out. And so the last choice that they have before they start getting into matching only one of them is State and Mercy. And luckily that works for them. David at State, Aaron at Mercy. David now outplaces Fred. And so Fred gets placed out of State. And Hassan and Aaron both place at Mercy. But now Fred is without a placement. He lost his placement at State. So Fred tries Mercy. But Mercy didn't rank Fred at all, which means Fred is not acceptable to them. And so Fred goes without a placement. The placements that we have are that Hassan placed at Mercy, Aaron placed at Mercy, David placed at State, Elena placed at City, and Phoebe placed at City. Okay. All right. Let's keep going. Number 9. In class, we did an example of a round-robin tournament with 6 teams to show that K6 has an edge coloring with only 5 colors. So this is K6. There you go. All those edges are drawn. And then this is K5. It only has 5 vertices. Yeah. And even though K5 is a smaller graph, it still takes 5 colors to color K5. We can't do this with just 4 colors. So what was the argument here? So if I think of all of the vertices as teams and all of the edges as matches that the teams have to play, we have 6 teams, which means 6 choose 2 or 15 matches to play. And because we have 6 teams, we can play 3 matches simultaneously. And 15 divided by 3 means it will take 5 rounds are needed. And we learned on Monday, that each round can be a different color, and then that would create an edge color in front of graph. And so that will be 5 colors needed as well, 1 per round. So what if we tried this argument with K5? There are only 5 teams, and so 5 choose 2 is only 10 matches to play. But with 5 teams, we can only play 2 matches simultaneously. Which means every time, 4 teams are playing 2 matches, the 5th team is sitting out. And 10 divided by 2 is still 5 rounds needed. And so that's 5 colors needed. So even though we have a smaller graph, we do not gain any efficiency in being able to schedule tournaments, because with 6 teams, all of the teams can be playing simultaneously. With 5 teams, only 4 of the 5 teams can be playing at any given time. So, all right. So, anyway, so this is using the similar argument to what we did in class, or in the video. All right. So let's look at number 10. A connected graph with 7 vertices has an edge coloring with only 2 colors. Prove that G must be isomorphic to this graph. All right. So first step is by Ising's theorem. If only 2 colors are needed, then the maximum degree of any vertex is 2. Okay. There are only 2 kinds of graph that are connected and have max degree 2. There are only 2 connected graphs with maximum degree 2. One is a straight line graph, and one is a cycle. But we're told that only 2 colors are needed. Cycle can't be completed using only 2 colors. Let's see that argument there. So if we make this edge blue and the next edge red, the next edge blue, next edge red, you got to see what's going to happen is because we have an odd number of colors, or sorry, not an odd number of colors, an odd number of edges. This last edge can't be blue and it can't be red, and so we're forced into using a third color for that last edge. And therefore, since there are only 2 connected graphs with max degree 2, and a cycle requires 3 colors, therefore, by elimination, we have to have the line graph. So those are the steps in the proof. Use Ising's theorem to show that the max degree is equal to 2. then used the fact that there are only two connected graphs with max degree of 2, and then used the fact that a cycle is not two colorable to eliminate the cycle as one of the two possibilities. Okay. So let's take a look at number 11. Suppose every vertex in a graph had degree 3 or 7, or according to Ising's theorem, what are the possible number of colors required for edge coloring of G? If there is a degree of vertex, if there is a vertex of degree 7, then Ising's theorem says the number of colors is 7 or 8. That is, if you go from the degree to the number of colors, is either the same or one higher. And so that's what we get. Now this says, suppose every vertex had degree 3 or 7. That doesn't say that we have to have a degree of 7. And so if there are only vertices of degree 3, then the number of colors is either 3 or 4. Okay? All right. Number 12. Give the number of faces and the side length of each face in the graph shown below. So a face is a region in the plane, a separate region in the plane. So we have this region here, we have this region here, and then we have this region out here that goes all the way around the shape. The outside always counts as a face. And so there are a total of 3 faces. Let's go back to black. I'll try that. So what is the side length of each of these faces? So the side length of this interior face here is 3. There are 3 sides, 1, 3. That's pretty easy. We learned that in kindergarten. This face has a side length of 6. The trace around the boundary, we have to go through 1, 2, 3, 4, 5, and then back. We have to traverse across an edge 6 times to get around the entire face. This particular edge here, we have to traverse twice. So this has a side length of 6. And then the last one, if we traverse around the boundary, we're going to go through 1 edge, 2 edges, 3 edges, 4, 5, 6 around the triangle. Back across the bridge is 7, and then 8 and 9, and that gets us back to the starting point. And so the last face has a side length of 9. Okay. So that's all we have to do for that problem. Pretty easy. Number 13. A graph has 4 faces with side lengths 3, 4, 5, and 8. Those numbers add up to 20. One of the things I want to point out from the previous question is that every edge got counted twice when we counted all these side lengths. If a edge is separating a face from another face, it got counted as part of the triangle and as part of the exterior face. And these 2 special edges here, this one here that doesn't connector and interior got counted going forward across the bridge and again backwards across the bridge. So it got counted twice. And this edge here got counted twice because we had to go out and then back across that edge. And so every edge gets counted twice. And so if I count every edge twice and get 20, then there are only 10 edges. Okay. So that's 13. A graph has 6 faces and 14 edges. We have a formula that relates the number of vertices and faces and edges. Says that this total always equals 2. And so if we know that the faces is 6 and the edges is 14, then we can solve for the number of vertices. And in particular, we need for these two to add up to 16. So that 16 minus 14 would be 2. And so V has to be 10. All right. And last question, number 15. A graph has 20 vertices, each with degree 6. Explain why G cannot be planar. So we have a theorem that says a connected planar graph has a vertex of degree 5 or less. Now, this doesn't say that G is connected, so let H be a component of G. That H has a vertex of degree 5 or less. But since H has a vertex of degree 5 or less, G has a vertex of degree 5 or less, because all the vertices in H are in G also. So let's say vertex V, then since V is also in G, G has a vertex of degree 5 or less. All right. I hope this helped. I be in touch with you again Monday. Good luck on the exam. Y'all take care.